is converter and its application in the domain of green energy. Is it audible properly? Hello?
Yes,
Is it
sir.
audible properly?
Yes, sir. Yes,
Yeah,
sir.
yeah. So now the topic is fundamentals of model order reduction techniques and their applications. And the topic of this training program is modeling and control of Paul Electronics converter along with the green energy applications. So in this, there is no terminology of model order reduction. So can this model order reduction connected to this domain? Because it is a modeling and control. So modeling means, as we think about modeling from control point of view, we say a transfer function modeling, state space modeling, and when we talk about the controller or control, we say P controller, PI controller, PID, lag, lead, and when you go to the next level, we say advanced controller, that is pole placement, LQR, H infinity, QFT. So there are so many uh, control techniques are involved, and then control is to controlling of any machine, any device, anything. And when we talk about the here converters, so we have DC to DC converters. Then we have inverter also. So in DC-DC converter, we have buck converter, boost converter, buck boost converter. So all this modeling, control, and converters, they are interlinked with this green energy applications. So again, the thing is that where is the role of this model order reduction techniques is coming. So we see how can we connect to model order reduction techniques to this the topic of modeling and control of power electronics converters. Slide is not okay. So now we talk about the model order reduction techniques, whether it is useful in research or not. So you can see these research papers, and I think that you can see this model order technique is not it started. You can see the 1995. Although this area started earlier, but you can see the state space models and order reduction of DC-DC converters into discontinuous mode. Then you can say power stage of fourth order DC converter by means of principal component analysis. Then here singular perturbation modulation of power electronic circuits. Then you can see the reduced order model for inter-inverter oscillation in an islanded group control microgrids. So no reduced order small signal model of three-phase PWM rectifier and its application in control system design and system analysis. So there are few papers I have just shown. So this indicate that one important thing that the researchers have used this model orderation techniques in the application, and particularly we can see that the application are showing in these power converters. So how they are using? So what is the logic behind it? So try to understand how the thing has come out. So here one model which I am showing here, a numerator 10, denominator is 1710, and we have this plant, and this is plot by MATLAB. So 10 square plus 7s plus 10. This is the transfer function model, and you can see this is the a Nyquist plot, and if you take half portion, we call as a polar plot. And ultimately, just looking after this, you can say that the system is stable. And then as I said that we'll join the some half portion that indicates a polar plot. So you can see this is a polar plot. And this is a frequency domain, and now we coming to the same thing in this way. 16 divided by s square plus 0.8 s plus 16. And if we compare with the standard second order model, that is omega n square plus s square plus 2 zeta omega ns plus omega n square. This omega is undamped natural frequency, zeta is damping factor. So we find that the zeta is 0.1, the omega n is 4. So this is the second order model, and earlier there was also second order model. And we got this type of plot. And then we have found out the roots of this denominator, and we've observed that for this the roots are, or we can say poles are minus 0.4 plus minus 3.9799. So this system we can call as a stable system. So system is stable, second order system. Now we just think over about the model which is second order. Can it possible to have a first order model for this system? So zeta is 0.14. So how can we think over it? And we have to think in two domains, a time domain as well as the frequency domain. So we've observed that the response of this model is like this. That is, some oscillatory behaviors are coming, and this oscillatory behavior is because these are complex conjugate poles here. Because this complex conjugate poles, so we will say that there are oscillatory behavior and it can under time response. So here we observe that we have taken here zeta equal to 0.1 damping factor. Now for this particular plant, now we think about some changing the values of zeta. So if you change the values of zeta, the damping factor, let us say, change to 0.5. So now we change the damping factor 0.5, and we are seeing the response in three ways. One is with respect to poles and zero plot, other with respect to polar plot or Nyquist plot, and then this is the response. So the theta 0.5 is 0.1. So what changes has happened in both these results? That is, when we are increase the damping, what is the observation? So you can see that when the damping is, the pole's position is here. You can see the pole's position, this arrow cross marks. And when we change the poles, zeta 0.5, you can see the pole position. Naturally, you observe that this poles are moving away, till away. And you can see the Nyquist plot. So Nyquist plot is like this. And this response is this one. So earlier we have some oscillating response. No, because that zeta change to increases the response instead of oscillative response, so that oscillative behavior reduces. So anyway, zeta 0.5 you have got this. This is the observation. Now when we take zeta equal to 1, so what is the observation now? When zeta equal to 1, earlier poles are very near to the imaginary axis. Then we have zeta taken 0.5, and then these poles which are on the imaginary axis now converges to a a single point. So you can see that there are two poles at one locations. I think in the control system, you might have studied the critical dam system, critical dam. So now we get to this type of phenomena. The system is a critically damped, zeta equal to 1. So we can see that way when we have a very low damping factor and there are two poles. So assume that the two poles are just like two friends. The two friends are like this, and or we can say they are very near, and then zeta increases from 0.5, 0, 0.1 to 0.5. Then they are moving away, and zeta equals to 1, they are at the same locations. So assume that now the two friends at zeta equals to 1 at the same location, they are staying here at the same point. So now if you see, if you increase the zeta again, what will happen? So now you see when we increase the zeta from 1 to 1.5. So two poles, just like I said, two friends, they are at one position, that is that they are living at one place. But as zeta we are increased from 1 to 1.5, if you talk about the poles are moving away. Just like that, two friends are moving away. Assume that one friend at say Roorkee and other it at Jaipur. There are two locations, Jaipur. Two friends are there and they are separated. So now there is a communication is online communication. They cannot stay because now zeta increases. But you can see that time the response of this. You can see the plot, that is the Nyquist plot, and this response. So you can see the earlier response when zeta equal to 1, that is the critically damped system. And when zeta increases to 1.5, we see that there is a some sort of slowness we can observe, and you can see this plot. So what is the observation in this all these figures? Let us say zeta equal to 1, zeta equal to 0.5, and zeta equals to 1, and zeta equals to 1.5. What changes are happening, particularly in this Nyquist plot? Here, what we observed in case of the pole zero plot, we can easily observe when zeta is less, poles are near to the imaginary axis. When zeta increases, poles which are complex conjugate move away. When zeta equals to 1, they are at one place. And after that, after zeta increases, they are separated. That is the observation. And here, the response becomes slow. Response becomes slow. So here, what changes is happen in the Nyquist plot? Can we see the similar type of Nyquist plot? So what changes happen? You can observe. And then we can say about it, this plot, particularly Nyquist plot. What is the observation in this plot as we changes the zeta value? Anyone can speak? Nitish Verma, I think it's speaking. Nitish Verma? Hello, Nitish Verma? Can you speak? Any student or any faculty or anyone?
Sir, all are on mute. I will give permission to everyone to speak in order to speak to you.
Okay, you can, yeah. Uh, any student can, is it possible to speak?
Yes, sir. Yes, sir. I'm making everyone, I'm giving permission
Yes.
to everyone.
Yes, yes, you can make it. Yes, anyone can speak about this point. What is the observation, particularly related to your Nyquist plot when we are increases the zeta?
Sir, it is like moving towards the origin. That is what I can observe.
Okay, what happened? Zeta increases.
It is moving, the Nyquist plot is moving towards the origin. And maybe possible it will be crossing the origin and towards, it will be going towards the ideal side.
Okay. So I can see, what the thing is that you can see the shape of this on the left hand side. Please see this shape, zeta equal to 0.5 and zeta equal to 1. So that means what Nitish is saying, this part, this bulging portion is moving towards the imaginary axis. Is it correct, Nitish? Hello, hello, Nitish.
Yes, sir. Yes,
Huh?
sir. Yes, sir. Yeah.
Correct, na? So are you student or faculty member? Hello, Nitish.
So I am the faculty, sir.
Okay, from which college? Which college?
Sir, I am from Government Engineering College, Bilaspur. That is in
Okay,
Himachal.
very good. Okay, very good. So we can see that this portion reduces and they are moving towards the imaginary axis. So zeta equal to 1, zeta equals to 1, 5. Again, you can see the region. They are again moving towards the imaginary axis. So now, zeta equals to 1, 5. Just like I say, two friends, one is at Roorkee and other is at Jaipur. And now we increase the zeta to 2. So that the zeta increases, now one pole at Roorkee, instead of Jaipur, it goes to Raipur now. It goes to now Raipur because now the separation is more. And you can see this bulging that also reduces. You can see here, this is the shape, zeta equal to 1.5. And when zeta equal to 2, you can see this type of shape. Poles are separated and again response is very slow. Now we change the zeta to 3. Zeta equal to 3. You can see the earlier when zeta equals to pole position is here around minus 15 second pole and here around say minus 1 or minus 2. And when zeta equal to 3, now the poles coming to minus 20 around minus 24. That is, instead of Raipur, it goes to now Mumbai, zeta equal to 3, and then the bulging is like this. And now you can see the zeta equal to 10. Zeta equal to 10, one pole at Roorkee, and another pole has moved away from the India, maybe out of country. So that is the source separations. So you can see that as the zeta increases, separations are more. And ultimately, you can see this response. And here you can see the response of in a Nyquist plot or polar plot. There is no bulging, a completely a path, and this path is not moving to the left hand side of this plane, S plane. So with very high values of zeta, you can this one, and as the zeta lower, bulging will be more. So what this indicates? So now poles are separated, they are far away. So that means there is no connection. What does indicate? So these indicate that everything is independent now from these poles. Response is low. And if you draw the polar plot or Nyquist plot of a first order system, if you draw polar plot and Nyquist plot of a first order system, you can get this type of performance. Same performance. That means your system is second order. You increases the damping very high value. And now for higher values of damping, the response in Nyquist plot is same as first order system. So that means what happens here? Here one pole at this location, another pole at this location, means as poles are very far, we can say, have more and more distance, the effect of one pole that is particularly the pole which is very far away from imaginary axis, that are very negligible, only response because of the poles which are nearer to the imaginary axis. So you observe that one pole at this location minus 0.2, another as minus 80, they are far away. So effect is less, and this indicate your reduced order model. Actually, what we are done, we are converting a second order plant to a first order plant, and this is possible by discarding the poles which are far away from the imaginary axis. So this minus pole which is at 80 will be discarded, only these poles will be remain, and we can get the reduced order. And why I'm saying, and this is verified in the frequency domain also, because in the frequency domain, the bottom portion we can show here, this bottom portion, this is the plot of first order system. You can draw any polar plot of a first order system. It will never cross the left half plane. It will be like this only. So this is about the reduced order model, that means discarding the poles which are far away from the image axis. And moreover, what happened, the poles which are far away from the image axis, if you see the time constant value, the time constant is very small. So that means if the time constant is very small, the system reaches to steady state very quickly. So the time, and whereas the poles which are very near to image axis, there are very high, more value of time constant. So that take more time to reach the steady state. So that way, we have to discard the poles which are very small time constant, because the main performance is contributed by the poles which are nearer to the imaginary axis. So this is the basic theory of the model order regression technique. So now you can see this example, 16 upon s square plus 10s plus 16 and 16, and now here you can see the numerator and this denominator s plus 0.2005 and s plus 79.77995. So that's the same thing. You can say here s minus 0.2005 and around it is 79.795. And while you said that, we are discarding this pole s plus 79 plus 9, and we got the result at 16 divided by s plus 0.2005. So now we see the Nyquist plot it. So now whatever thing what we have followed, that is correct. We are discarding the poles which are far away from the image axis. What this thing is that general shape is okay. General means there is no moment on other side. But here you can see that the original Nyquist plot showing like this, but the plot is of bigger size. Actually, when we say model orderation techniques, all the response should be exactly the same. But here we observe that if you talk the original plant and reduced order plant, although the general thing is same, structure is same, but the magnitude is very high. So the magnitude is high, means the reduced order model cannot be applicable, because what we want, what is the performance of the original model and the performance of the reduced order model must be same. So based on the theory, we see that this s plus 100 has very small time constant, which are very, so we are neglecting here and keeping only the dominant pole here, s plus 0.2, and the response of gs and gr of s should be exactly the same. But here this is not happened. And that means the shape is okay, first order system shape, but the result is not matching. So what can be the reason behind it? My question is correct. Hello, students. Hello, Dr. Nitish. Hello, am I audible?
Yes, yes, you are audible, sir.
Have you understood this, what I'm saying?
Yeah, yeah, yes, I understood.
Understood. Now you can see that I have discarded the non-dominant pole, and so what we want that the response should exactly match. Theoretically, we have seen everything, increase in damping, but when we are comparing it, you can see that shape is not matching. And again, I have checked by some other way. When I have determined the step response, time domain response, in a time domain response of the original system, they reaches to steady state at 1, but here steady state is 80. So you can see the shape is matching, but the steady state is a problem of the steady state. Steady state response, these are issues. There is no transient issues. So conceptually, we are correct. We are neglecting the poles which are far away from the imaginary axis and keeping on the dominant poles. But that means here, if you see the response on a one plot, they will not match. There is a difference. Hello, K. Ramesh. Am I audible? K. Ramesh. Hello, Dr. K. Ramesh. Is it okay? Is it, any reason behind it? Anybody can tell why it is happening like this?
Sir, one thing what I can understood is like pole is very much near to origin. So that is what it is making the system response so sluggish.
Okay.
I don't know exactly, but might be the reason.
Okay, the poles near to that makes sluggish. That is correct. Because the poles which are far away from the image axis, that effect we are discarded. This, uh, that means we have not taken into account, and the shape coming same. Hello, Dr. Nitish.
Yeah, getting it, sir.
Yeah, the shape coming same. You can see the original shape is just like you draw the polar plot. It looks same. Okay. So discarding the poles which are away from the image axis, the response should match. So what is the reason behind this? So the answer for this is that the reduced order model, it is okay. We have to discard the non-dominant pole, keeping only the dominant pole, but the effect of that non-dominant pole, we have to merge in the dominant pole. That is basic. We cannot discard anything like this. That some effect is always there. Some effect will always be there. That effect has to be merged, and then we can get it. Although the effect is minor, but the effect is to merge because something has always been there. So we cannot discard any pole like this. This is my view. Is it correct, my view? What I'm thinking like this at the juncture point? Means we cannot discard this S plus 79.5. Although we discard, but there's some effect is there. That effect we have to merge. Hello, Dr. Nitish.
Yeah, sir, getting it, sir. It has to assist. I got the
Yes.
point. It is showing some assistant, so that is very much negligible, but it is showing some assistant to the pole to which is near to the origin.
Yes. So my
To
point
merge
is
it.
that effect is there. The effect is because of this 79.79. There is a magnitude is there. That effect of that magnitude little bit we have to merge. That means what we want, we not only want a transient should match, as well as the steady state should also match. You can see that the steady state of the original plant 16 divided by 16. If you apply the step input and the step input using your the final value theorem, you can find out that for GS system or step input of RS, the response should reach to 1. So you can find that this is the response of the original plant. Okay. But what happened? The response, because of this, if you neglect this one, only 0.2, so that effect to be merged. So here we can see like this. So 16 divided by S plus 21 plus 18. So steady state is 16. So now the steady state of this reduced order plant, so steady state error is 16 divided by 0.8 is around 79 something. So now what happens? The steady state of the both the system should match. So the steady state of the original system equal to K multiplied by steady state of the reduced order model, because steady state should match. That is here. And then from this you can just give values, and the reduced order model become 3.2080. And if you draw, and now if you determine this, or now if you merge the steady state of this in the reduced order model, you will get 3.2 something, and then you can see the response of this both the system will be matched. So in this way, the step response of the both the system will match, and we can get the same response. Although there is a minute error will be there. So here you can see that both the responses is a match, but there is a minute variation is there in this case. That you can see the 0.956, 0.9565, 9.55. This small variation, but just looking at the overall way, you can see that the response should match. So the technically what to do now, reduced order modeling is that you have to discard the non-dominant pole, keeping dominant pole, and the effect of non-dominant pole should merge here. How to merge here? You have to determine the steady state of this original model equal to a factor K multiplied by the steady state of the reduced order model. From this you calculate this K, and K be multiplied with the reduced order model. And if you do this one, the response will match. So this is the concept of fundamental concept of model order reductions. I hope it is correct, Dr. Nitish.
Yes, sir.
Is it okay?
Can you just please explain it once again, sir, please?
Hello?
Sir, can you please explain it once again, sir, please?
Okay, I would like to explain. For example, let us say we have transfer function 10 divided by s plus 1. 10 divided by s plus 1. 10 divided by s plus 1. What is the steady state of this? If you apply step input, okay, just a minute, I can show this MATLAB program. MATLAB is visible to you? My MATLAB program?
Yes, sir.
Okay, so now what we will do here, I am taking numerator equal to say 1 and denominator equal to say convolution of say 1 1 comma 110. So I have taken one pole at s equals to 1 minus 1 and another pole at s equals to minus 10. That is sys equal to transfer function numerator comma denominator. This is a transfer function. Is it okay? 1 divided by s square plus 11s plus 10. Is it correct, Dr. Nitish?
Yeah, yes, sir. Yes.
Okay. So one pole at -1, other at -10. So -1 is the dominant pole, -10 is non-dominant pole. So now this is the transfer function. Now if you determine the step response, step S-wise. Okay. So you can see that what is the steady state value is 0.1. Is it visible? 0.1, is it visible to everyone?
Visible, sir.
Yes, sir.
0.1. So how you got 0.1? You can see if you replace S equal to 0 here, 0, 0, 11, 0, 1 by 10, that is 0.1. Okay, that is a steady state value. Direct, we can imagine directly or we can identify directly just looking at a transfer function. Just like this, I will write one transfer function numerator equal to 10. Say numerator 1 equal to 10. Earlier I have taken 1, I have taken 10. Sy is equal to transfer function numerator 1 comma denominator. You can see what is the transfer function now? Is it, can you read it? 10 divided by
S
S
square
plus
plus 11.
11s plus 10. Okay. Hello, Dr. Nitish.
Yeah, sir.
So now we are applying determine the step response for this step response. So I will write comma step SYS. So you can see 10 divided by 10,
1.
1. See well. Hello, Dr. K. Ramesh.
Yeah, tell me, sir.
Is it okay?
Correct, sir, correct.
Okay, 1. So now this is a second order plant. I want to determine the response. That is we have to reduce the model to first order. So the first order pole is at S plus 1. So now we will determine reduced order model. So we discard 10, keeping only 1. So now we can see my numerator is 10 now. So my denominator is changed. Denominator is 1, 1 only. 1, 1. Because 10 we are discarded. So now my transfer function is SY1 transfer function. Numerator 1, denominator 1. So now 10 divided by S plus 1. Earlier transfer function involved S plus 1, S plus 10. Now here transfer function is 10 we have discarded. 10 divided by S plus 1. So now original system is SYS1, SYS1. We write a hold on command now. Keeping original response as it is, hold on. Now we write state SYS1. So you can see, now you can see, observe. What you observed? Original response, steady state is 10. Reduced system steady state of 1. Why it is called 1? You can see, sorry, 10 by 1. The reduced order model has steady state of 10, and reduced system has steady state of 1. Is it okay now? You can see 10 by 1. If you apply step input to reduced order model is 10 divided by S plus 1. So steady state will come as 10. You can see this 10, this value 10. This is the response. And original system has steady state of 1. So now the steady state of both are same. Then what to do now? So what we'll do, we will take the steady state of the original system equal to 1, k multiplied by 10. So k equals to 1 by 10. So if you multiply the reduced order model by 1 by 10, so here we write S by S1 equal to transfer function 1 by 10 star numerator 1 comma denominator 1. So, and now we find the step of SYS and SYS1. you can see now. So now steady state of in the original reduced order model plant, 10 we are divided by 1 by 10 and you can get 1 plus s plus 1. That means reduced order model is 1 divided by s plus 1. You can see the response is matching. See original plant and reduced order plant. So SYS1 is original plant and SYS1 is the reduced order plant. I hope Dr. Nitish.
Yeah, sir. Very well understood, sir. Very nicely explained.
Clear enough? Conceptually clear what actually we did? The steady state we have matched. So we cannot discard the poles which are crisis. That means, let us say, as you said, two friends, they are moving separate to each other, but it is not like that. They are completely separate. There is some mutual connection or something is there. So that mutual connection is there. It is in a control. It is with respect to steady state, transient and steady state. Okay, Dr. K. Ramesh.
Yeah, clear, sir.
Okay. Okay, now this is the basic theory. So now this is basic theory of reduced order model. So now we can see what challenges which will come to us. Because now here we have taken the poles which are separated from each other. One pole are nearer, others are far away from the measures. But if this is the case, suppose system is represented by 9, 6 square plus 6s plus 9. And above equation can be written as GS equal to 9, 6 plus 3 whole square. What will be the reduced order model for such systems? Both the poles at the same location. Now here difficult to identify which is dominant pole and which is non-dominant pole. Is it clear now? Now our idea is that we haven't got idea about the model reduction by means of time domain, frequency domain, poles, that this is the Kane theory. But because there are many cases happen, the poles at the same location. Or when we call about the critically damped system, so our system is critically damped. So in particular, this type of cases, how can we apply the reduced order model? Pole at the same location. Hello, K. Ramesh.
Yeah.
Is it okay? Correct? My point?
Yeah, point is clear, sir.
Hello? Hello, K. Ramesh?
Yeah, clear, sir, clear.
Correct, na?
Correct, sir.
Okay.
So I have one question, sir.
Huh? Hello? Yes.
Actually, overall we have to make the step response like steady state response same for what we have used multiplication by k. So this is possible even the pole is at 1 and 2 location, s plus 1 and s plus 2. So when the pole has a location at 2, then also we can do this.
Actually,
we can obtain the same steady state response by the multiplication factor k.
Actually, 1 minute. I had to, because your voice is not clear. I'm just asking from a speaker for here. 1 minute. Because I'm not audible properly. My voice is audible properly to you? My voice?
Yes, sir, your voice is audible. Sir, my question is, suppose I am having a transfer function 10 divided by s plus 1 into s plus 2. Here also we can make the by neglecting the pole at 2 and multiplying with the
1 minute. Siddharth, can you come with the speaker from office? Speaker. Okay. Let us, yes, possibly bring that speaker because in the lecture is going on, I'm not audible. Okay, please. Okay. Okay, Nitish. Yeah. Yeah. Hello.
Sir, suppose the second pole,
Hmm.
let's say it is not at 10, it is at 2.
Not
The
at.
first, not
Uh,
at 10,
hmm.
and it is at 2.
S plus 1, S plus 2. Okay. Yeah.
Yeah. Then also we can make the response same by neglecting the pole at 2.
No. Just that's why I'm saying you. Okay. Just I will go through this original things. You can see earlier your zeta is 0.5. Okay. Poles are complex conjugate. Then zeta 1 poles are at one location. So now we can see that when zeta equal to 0.5, separation is small. So as the lesser the separation, the response matching will not be good. So response will match only better when poles are very far away from separation. So we can see that there can be a model, but it cannot be a good for a system point of view. What we want in moderation, response should be matched, or we can say that around in a general language, at least more than 90% should match. Because here you can see, just a bit, I will go with this. What your point? I will take one transfer function. Is it visible to you, Nitish?
Yes, sir, visible, sir, very
Okay.
visible.
1 minute. Is it okay? 1 minute. Huh?
I will connect.
Correct, just a bit. Correct. Okay. Wait.
Done.
Thank you. Okay, is it okay? Is it visible now?
Yes, sir.
Yes. Okay. So now I write it one numerator 1. Okay. Denominator we write down as formulation of 1, 1, 1, 2. Is it okay? You are saying same thing?
Yeah, yes, sir.
Okay. So what is happened? System equal to transfer function numerator, comma, denominator. So what transformation we got? 1 divided by s square plus 3s plus 2. Okay. So my steady state is 0.5 here, 1 by 2.
Yeah,
You can see
yes.
through distance. Step s by s. You can see it, okay? Here, 0.5. It is going towards
Yes,
0.5. Okay. So now I will hold this result. Hold on. Let's hold on. And now we have to resort a transfer function just as sys 1. Okay, I will write denominator as denominator 1 equal to 1, 1. Sys 1 equal to transfer function numerator denominator 1. Okay, so now my transfer function is 1 divided by s plus 1 because 2 are neglected. Okay, so now you can see the step s plus 1 you can see this. You can see that this is steady state problem as well as the transient problem also. Now you can see the transient. I will add some steady state. So for steady state, what I will do, I will write sys1 transfer function 0.5. star numerator denominator 1. Then step sys comma sys 1. Just you can see, observe this. This is the response of the original plant and reduced plant when we have neglected S plus 2. You can see the difference. So this is not a matching. This is not a matching. So we cannot accept this result because it's not about that there is an exact matching of the original model and reduced order model. Hello?
Yeah, sir, I understood. This should be at least more than 90% matching, sir.
Yeah, so, yeah, more than 90%, because we should match. Because now the results are different now. Results are different, responses are different. So if the results are exactly matched, just now I will take this again problem. So what happened? I will take say SYS1.
Sir, what is the thumb rule of identifying the dominant pole?
Okay, so we can see that the dominant pole, these poles are very near to the imaginary axis. Imaginary axis. Say 0.1, 0.2, 0.3. Okay. And non-dominant pole means which are very far away. In other words, which has very small time constant. System which is large time constant is called dominant poles. And the non-dominant pole generally we say 4 to 5 times of the dominant poles. Okay.
Okay, sir.
Okay. So now for the same problem, I can show you the result which is matching now. So I will take here S plus 1 numerator equal to 1. Denominator equal to convolution of say 100. I will take 100 now. Okay. SYS equal to transfer function numerator comma denominator. This is one transfer function, and that is we have transfer function 1 divided by s square plus 100 and 1s plus 100. And now we take the reduced order model. Denominator equal to denominator 1 equal to here 1, and here SYS 1 equal to transfer function 1 divided by 100 multiplied by a numerator comma denominator 1. Numerator comma denominator 1. Here step SYS comma SYS 1. Now you can see the response. See, both the plots are there. You can see SYS is prime. Hello, Dr.
Yes.
Sir, I
You
have
can see it. Yes.
Yes, sir. Sir, when we are removing the dominant pole, should we have to make steady state gain equal in both the cases or the DC gain equal? Means, is there any difference between
that's
steady
it.
state gain and DC gain?
Same thing.
Okay. Okay, sir.
Same thing. Okay. So now coming to the other challenges. Now we have just observed, and now Dr. Nitish has asked me, what about S plus 1, S plus 2? Now my point is that can we reduce the model if of 9 divided by S plus 3 whole square? How can it reduce the model of this nature? Because pole at the same location. Then we have seen, we have taken the reduced order model that 9y s plus 3 whole square. We have got this response. Somebody says, remove this s plus 3. We have got this response. And this is the observation. So this is the one phenomena. Second phenomena is that if your system is unstable, if your system is unstable, then can it possible to reduce the model? That means we have three poles, one at -1, -2, other at +10. Can it possible to reduce the model for unstable system? Then second point is that your original system has a underdamped response, highly oscillative response. The reduced order model has very good response. Can we take it? So these are the various challenges of the reduced order model techniques. And therefore, to solve this type of problems, the various techniques have been developed. And by means of these techniques, we can reduce the model. My point is that if this model of this one 1 by x plus c square, the researcher had developed the concept to reduce such type of models. Hello, Dr. K. Ramesh?
Hello, sir.
Hello, sir. Hello, is it okay what I'm telling here? My point is that, hello?
Yeah, clear, sir.
Clear, na? In the poles at the repeated poles, maybe at 9 plus s plus 3 raised to 10 poles are there. Still, the researchers have developed some concept, some logic to solve this problem. So, that type of work has come in the literature and that published in the top journal. Now, I would like to come about the one important issues about the practical feasibility of this. So you might have heard one terminology, a controllability and observability. All the scholars and professors have gone through the word controllability, observability of the plant. In advanced control, if you want to design a controller, you have to go with one test. That is, system must be controllable and even observable. Or particularly for pole placement, controllability test is required, important. And system must be controllable. So now we can see the fundamental concept of this model relation with the concept of controllability. Dr. Nitish? Hello, Dr. Nitish?
Yes, sir.
Have you gone through the concept of controllability?
Not much. Little bit I know that is the basic, like the observability,
Okay.
that any instant of
Yeah.
time for a particular parameter can be observed and it can be controlled.
Yeah, correct. So what happened? This is the transfer function. Now we think this time in terms of state space. In terms of state space, means there are states are involved. Just like there are three poles. In a state space, there are three states. I think this point is okay for everyone. 3 poles, 3 states. 2 poles, 2 states. Now we think this type of problem from advanced control point of view, fundamentals from advanced control point of view. So now you can see you have a system 2. You can see the MATLAB program is also done. This is system 2. And this is the system 3. And system 2, system 3, and we got the response. This is the response. And here more or less is matching. Although we expected more matching. But here we rejected this S plus 6 pole. And its effect is merged in the reduced order model by taking steady by 1 by S. And then you can see that instead of the 6, I have taken 12, S plus this 12. And we obtained the reduced order model. And in the reduced order model, we have taken S plus 4, S plus 2. And this 12, we have taken 1 by 12, that is to match the steady state. And we got the reduced order model as 0.083 S square plus 3S plus 2. That is the reduced order model. And then, so now what we think, now it classical control and advanced control. And here the topic is mentioned about the modeling. So this modeling, transfer function, I think both are important. So then what we have done, we have converted this transfer function 1 by s cube plus 50s square plus 30 to 24 into a state space form. And this is called comparative form of model. So 0, 1, 0, 0, 0, 1. And the elements here the elements were written in terms of minus 24, minus 38, minus 15, x for h to x3, and output is y100. So this is the we can say a state space model from the given transfer function. So what is the transfer function and what is the state space? Those are learning for the first time. Transfer function means we have input and output. We don't know what's going on internal. State space means what is going on internally. That is called a state space model. We know all internal things. So transfer function is comparatively better because we have to think about input and output. State space means along with input and output, whatever the internal things we have to take care of. It's just like a suppose I have some health problem, I will go to doctor, a nearby doctor. I will say I have this problem with this problem. Doctor will give the medicine. Okay, so he will not do any test. Whatever I have told, based on this he prescribe the medicine. That is called transfer function, input output. State space means the doctor say no. What you do? I will not prescribe medicine right now. We will go for some test. You say urine test, blood test, cholesterol. So many tests are there nowadays. So we have to go with all these tests so that the internal information are available. My input is also there. Based on the output, that is called state space. That is called advanced control. So now what happened in a control? This control, this advanced and classical and advanced are interrelated. That means the model which is in the state space, the transfer function, we can convert into a state space. So you can see that this is a transfer function, and we can convert into state space model. That is H dot. This is A matrix, B matrix, and C matrix. So now what happened? If you now determine the response of this transfer function and state space, you can say that you can get exactly the same response. System 2 and the advanced one means this is the model. You can see that there are exact matching. That is, there is no issue, 100% matching is there with respect to system and the state space model. So the participants, because I can see two names here on my screen, so I am calling this. Any other can also speak. So Dr. Nitish. Dr. Nitish.
Yeah,
Is it
sir.
okay?
Got it,
Clear, no? This point is clear, no? So I have determined, and we got the same thing. Now I have done the reduced order model here for this 16.3, 0.083, S2 3s plus 2. And here we have determined this state space model. Okay. And here 16.2 and 16.3. And still it is more is a one of the matching response we can observe. So then we have taken the original model, and this is the reduced order model. That is both the state space model now. Whatever classical control model, we have changed to a state space model. Both are state space, and results are exactly matching. Actually, sir, minor variations are there. So what happened here? X1 dot, X2 dot, and here X1 dot, X2 dot. Two states are there, and we are left the third state. Third state is missing in this problem now. In transfer function, we are talking about the poles. In state space, we are talking about the states. Out of the three states, we keep only two states, X1 and X2, and the results are matching. Now we see that X3 is there. You can see system 2, system 1, and okay. Now what we have done, this is my transfer function, state space model 0, 1, -2, -3, x1, x2, 0, 1. And here x1 dot, x2 dot, x3 dot. So what happened? The state is missing. So now if you replace all this by 0 and 0, because they're actually 0, 0. Because state is missing means they are connected with these values of zeros. 0, 0, 0, and this is 0. x1, x2, x3, 0, 0, 1, 1, 0, 0.
Sir, is
Hello,
the
Dr. Nitish? Yeah.
B
Hello?
matrix is the B matrix is the second quantity 1 instead of 0, 0, 1? Should it
Yeah,
be 0,
yeah,
1,
okay,
0?
I have missed. Okay. 0, 1, 0. Okay, okay. Just I have missed it. Okay, I have
Okay,
missed
sir.
it.
Okay, sir.
Okay, I just miss it. I can write 0, 1, 0. No? Yes. I just miss it. I write 0, 1, 0. Okay. So now this is the A matrix and B matrix and this one. So yeah, in my programming, I have written correctly. Okay. Hello? Can see? Yeah, 0, 1, 0. Correct? Yeah.
Yes, sir. Yes.
So now if you determine the controllability of the system, you have to check the controllability of the system, whether system is controllable or not. But this way, because here we are not taken, we are completely removed. We are not taking into. We assume that only 2 states are there, and but there are, we assume that there are third state, and third state has no effect. They have, okay, here also actually should be 1. Sorry, I have taken 1. Okay, here x2 dot, here it should be 1. Just now I was showing you. In the programming, I have it correctly. So now about the controllability of the system. One state is missing. So the advanced controller say that you can design the controller. We can design the controller only when system is controllable. If the system is not controllable, we cannot design a controller. Or controller can be somehow designed, but practically they have no impact on the results. Because now this is all established theory of the model relation. There are more than 10,000 research articles in the domain. They have converted a original model to this sort of model into as a function. Now, as a researcher, I thought, can you think about the advanced control point of view? The advanced control I have converted into state space, and this is the obtained, and this indicates that there is a problem of the controllability of the system. So, what is this issue though? How can resolve this issue? Papers were published, everything is there. Here we are, just one of the state is missing. Because what happened? Transfer state space, transfer function we are converted to state space. Because all the theory of transfer function is applicable to the state space, particularly from stability point of view. Dr. Nitish, is it correct? What I say?
Yeah. Sir, correct, sir.
If you take the in a transfer function, stability depends by the poles. In a space, stability depends upon a matrix. Okay. So both are safe. So that means whatever we think from the model relation point of view, that should be applied here. But here we can see that the states are missing. So in the state is missing and rest are the 0, 0. If you check the controllability, you can see that what result will get. And but the next thing is that mathematically, if you not keep that x3 here, there is no problem of the controllability here. There is model x1 dot x2 dot 0, 1, -2, -3, x1, x2, 0, 1. This system is fully controllable. There is no issue. But when you take x3, dot additionally and keep other elements at 0 because we are removing the state, something different will come out. In other words, something is good in state space transfer function, but may not be some challenges we observed in the state space. So now the thing is that how can we solve these type of challenges so that our system is practically a correct system? And you can see that this sort of model is very useful because what happened, because if you use this model automation as per the textbook or which is the article, it is said that importance of moderation in our system to have low order model that will simplify the understanding of the system. Again, it reduces the computational effort in the simulation problem. Then again, decrease the computational effort to make the design of the component more efficient. And again, we required a very, very simple control law. We require very simple control law. And that is very useful if we talk about the PID type of controller. If we talk about a PID controller, KP, K, and KD, if the model is very high, this PID term, KP, K, KD, control all the 100 poles. If the 100 order system we convert it into a third order poles, the KP, KD has to control only 3 poles. That's why they say that that is quite a very simple control law. Dr. Ravindra name is missing.
Yes, sir. Yes, sir.
Ravindra Kulu. My point is clear.
Yeah.
Suppose we have 100 order system is there. 100 order system brings to third order, and we design a PID control for third order and PID for 100 order. PID means KP, KID. KP, KID, KD. This 3 tuning parameter control the 3 poles. And suppose if PID has to control to 100 of poles, what is the better? So according to literature, it has been said that you have simple control law. Even a simulation time will be less. And then the system becomes simple. That are the advantage of this model ordination techniques. But along with the advantage, I have told about some challenges. The challenges, first challenge I have told you that about this S plus, if the poles at the same location, how to solve this problem? The second problem I told, if the system is unstable, can it possible to use the model? The third point I have told you about this, when you think about the controllability observability in terms of state space, advanced control, classical control to advanced control. There is although we cannot comment something what is happening, but here, if you do like this arrangement, this one 0, 0, 0, 0, 0, one state is missing. And it is said that in advanced control, those participants who have studied the advanced control, in the advanced control design, it is clearly mentioned that system must be controllable, that none of the state is missing. But here the state is missed. So really it is practically feasible things. So this is also one of the challenge. And another important challenge about the response. Step response and the frequency response. So my point is that two systems, system 1 and system 2, system 1, system 2, both have same state response. System 1 and system 2 both have same state response. Can they have same frequency response? Hello, Dr. Nitish, my question is clear?
Yes, sir.
But my point is that two systems, they have same state response, exactly the same. Can we have same frequency response? Exactly the same. same step response? Can we get the same frequency response? Smith, SYS. Yes, we get same or different? Hypothetic waveform. Just layman think like this. We should get
So
same.
we can have it by multiplying it with some transfer function that can give us same frequency response.
No, if you apply transformation, means you are increasing the model then. You increase the model. Anyway, first of all, we see MATLAB. What MATLAB will give? Bode S5, hold on. Bode S5 What is happening? Is it visible? Hello, Dr. Ravindra. Hello, Dr. Ravindra.
Visible, sir.
Yeah, visible.
Visible, na? So you can see that both the plots, two plots, 16.1 and 16.2, they have both same state response. And you can see the response, frequency response. So you can see the frequency response. Okay, I will
Sir,
wait for the who is speaking?
sir, I have one question.
Yeah,
Sir, we get the same step response, but we get the different frequency response, right?
No, I'm just asking you because my point is I asked point
Okay.
that
Sir, I think we get different frequency response maybe because due to the different dominant poles.
that means in other words, somebody is working on the real time problem. Okay, somebody.
Yes, sir.
Because all three we have to apply for real time control system, right? Real time control system. Somebody working on a step response, he is not observing the frequency response. He only step response. So can we say that the response is optimized are perfect for our system? Because even this point is not connected to modularity, it is also connected to our performance also. Right? How? Because performance, because when in time domain, the response is matching, just like here I will show you again. State S5, comma S5 1 minute. Got it. You can see response. They are exactly matching. You can see there are small minor variations there. They are exactly matching. You can see there's no issue. But the same thing when you begin in the
हाँ पता कैसे पाएगा सर
you can see one minute Bode SYS and SYS, comma SYS. Just see it. Yeah, you can see the different phenomena is observed. So my point is that here you can get the different frequency, the frequency response is not matching. So you can see these are the various challenges of the model orderation technique. So what happened during that earlier time when researchers have solved this problem, because we often solution when we have some problem, if there is no problem, we'll not go with the research. No, research will come when some problems are there. So our aim is to identify some problems So now next is one of the problem I have told, the matching of this frequency response around the repeated poles, instability, controllability. So these are the various challenges which should be observed by the researcher in the long back. And this problem is not only connected to our model operation. This problem is connected to a control theory also, control application also, and that is also connected to this one. Because what my point is that the responses, because the responses differently, matching are not different. Actually, something is there. That's why when we apply, we design a converter and everything, when we do our work, how to, which type of response we should take, whether we take both the response or one is sufficient. So this problem is important from our other application point of view. So the point is that these are the various challenges which is observed by the researchers, and to solve these challenges, uh, the various the control theory has been established, or researchers have worked, particularly those working on a theoretical aspect. They have worked on the theoretical aspects, and they have anyhow developed a new theory which is can be applicable for all types of problems. Although the, the challenges are not the same, there are also some more and more challenges are coming. For example, we are taking a plant, let us say a plant that is a fixed plant. Your numerator is fixed and denominator is fixed. But in a real time, if you talk about that values, the coefficient point of view, the coefficients are not fixed. The denominator is also changing, just like our inductor. Inductor has small resistance. Okay, so as time changes, that also change. Then the input source, it has a battery resistance, that also change. So everything is changing. A transfer function is a linear plant that is fixed. So actually the plant there are variations are there. So in that particular case, how do we go for the model organization? That is also one of the challenges which to be observed because that are connected to our applications. So earlier I told there are various application of model organization in a power converter. You can see that in power system, electrical power grid. Okay, we saw the transformation from RLC network models for electrical power grid. You can see that in the electrical power grid, this type of modulation theory has been utilized. Here you can see that the modulation addition technique, electrical power system is then your automation for large scale linear oscillator system, they are also being used. So you can see the literature, there's so many applications, this modulation technique have been used. Sometimes they are used a simulation point of view. But really, if you think about a practical point of view, the challenges are just now I have told to you. So many challenges are there. That means the most important thing that when you go to industry, and if somebody would like to apply modulation technique, very useful. So what type of precaution to be made? So the one precaution we have seen, one point is that the most important precaution about the frequencies. You can see that in the plant, when we go for very high frequency range, there is a more variations. So in that case, how to use the modulation technique? Which theory we can develop? That needs to be addressed. So now these are some of the papers of the moderation. So the concept of the moderation has been started around 1966. You can see that A.G. Davison, Method for Simplifying Linear Dynamic System. In 1968 and 1960. Okay. So here the theory of the moderation has been started in the 66. And the theory of the state space, advanced control, it also started around that time, around 1960s time. So now, although we have some limited time, I cannot go with some methodologies. So now I will go with the simple methodology, and maybe it may possible that some parties are aware of it. But anyway, I can feel that some are they are not aware of it. So I am going with the one methodology that is model relations in Raoult stability criteria. I think the Raoult criteria, everybody are aware of it. Hello, Dr. Nitish? Dr. Nitish? Hello, Dr. Nitish?
Yes, sir. Yes, sir.
I think Raoult criteria is aware of Everybody are aware of Mott criteria? Routh
Yes.
criteria? Yeah.
Yes, sir.
So what happened in 1978, based on this Routh criteria, okay, V. Krishnamurthy, who was doing PhD from IIC, Indian Institute of Science, Bangalore, he has worked on Routh criteria, and he has proved that based on the modernization, based on the Routh criteria, we can reduce higher order model to a lower order model. What I'm saying, just like there are some problem challenges I observed, but in 78, this Routh, based on the Routh criteria, which we are used for the stability of the system. System is there, characteristic equation is there. We are applying the criteria and we just take the stability. If any equation is there, you have a Routh array. In the Routh array, if there is no sign change, we can say the system is stable. If sign change, system is stable. So this is for stability plot. But this particular Routh criteria, the Krishnamurthy, which was used in 1978 for model ordination. And most surprising thing is that the Routh criteria has been developed around 1877 time. And just after 100 years, of time, he has used this concept. So, whatever, according to my view, whatever theory is available in literature, never you can say that it is saturated or we don't know when the theory has been utilized for our work. And what my point is that the theory which has been developed in the past, they are very good mathematicians. They have developed very, very good theory. Even the theory of interval uncertainty, one Khato is there. He has developed the stability of that particular equations. So the point is that we must respect the old theories and use that old theories in our today's research work. So that theory of the Routh criteria has been developed in 1978. Method is based on Routh criteria. So how to determine the disorder model for this? He says simply, if your transfer function like this, say B11 SH2n, B21 SH2n minus 1, B12 SH2n minus 2, B22, and we have a numerator and denominator. He simply say, simple, nothing like this. You apply Routh criteria to numerator, Routh criteria to denominator, you can get a reduced order model. I think nothing simple as it is. And these were published in IEEE automatic transaction. I think you are aware. I think those who have done a PhD or pursuing PhD, they are aware of the importance of the IEEE transaction. Even if you can get a public IEEE, it as good as everybody say, okay, now it is on the verge of submission of the thesis, or he will definitely get a PhD. That is the importance of Routh, importance of transaction. So this paper is published in Automatic Control in 78, and it simply says that. So now here, these are the here we have to apply Routh criteria to numerator. So here numerator we applied and denominator, and from this we can get the reduced order model, whatever order we required. So now the example is like this. So this is the example of the 8th order plant. S7, S6, this is numerator, and this is denominator. This is proper transformation. And you can see that the Routh criteria is aware of it. So we have to write the elements. So 35, 138, like this elements has been written. And then the price of cross multiplication, which is given the Routh criteria. And we can get this first column of the Routh array. And the denominator, this is denominator transformation, SH2A 33, this is. For this, we apply this Routh criteria. And you can see that if you want the model, let us say we want the second order model for this. So this 5th order model and second order model. So what second order model? For denominator, what is there? 9600, you can see 9600, 18162s, and 201. This multiplied by this A0 means this one, SH0, this S1, and this S2. So that is the denominator. And for numerator, this 334828.S plus 1994280. So if you write this element here, and we can't go to this one. No need to calculate the no need to calculate the roots of the numerator. No need to calculate the roots of the denominator. Just simply applying the Routh criteria, you can get the reduced order model. Similarly, we have got a fifth order model. So by means of this, you can got the order of any order, seventh order, sixth order, fifth order, any order we can get the model, and you can see the response of the model, and it is said that the response is more or less, although if you go for the second order model, matching is not proper, but for a fifth order model, the response is more or less is matching. So this is the result given in the research paper of Krishnamurthy, which is published in 1978. By means of a Routh criteria, we can get a reduced order model of the plot. And this is a well-established result, published results. And you can see that during that time of 1978, there were no software, no MATLAB, nothing is there. And that time, this result has been obtained by Krishnamurthy. And without calculating any roots, poles, today we have MATLAB, really we can determine it. So this result has got a very high importance, or researchers have observed how can this result has been obtained on this. And then he has also given one problem challenges which is observed of how to determine the reduced order model for unstable system also. Instability problem has been solved. He said that in this paper, question of unstable system. For the unstable system, the method may fail since the first column of the elements of the out table are negative, because this method is only applicable when the first column are positive. If the first column is negative, this method cannot be applicable. So how to do it? So he said that in order to operate reduced order model for unstable system, so what he said,
Sir,
they need to
Sir, can you explain how he has reduced it to second order or fifth order using this?
Okay, just a minute.
Sir, I have also a question. How to know that, like, the model was originally eighth order, and you had shown that fifth order is somewhat showing more similar response. So how to know that how much we have to reduce, then we will get the almost same response? Means there has to be a trial and error, or there is any like this?
Okay. Anyway, I will ask both the questions. For first question, the question I will ask how to get the second order model. So now, who is speaking with me here?
Yeah.
Lady, the girl who's speaking. Hello.
Ravindra.
Ravindra, just a minute. This is you can see 20123 thought square 1811 S2 9600. Okay, this is the denominator. Okay, so now you can see the Routh array. This is you can say H2, na?
Yes.
H2. Okay, so the coefficient of H2 is 201123.s square into S. Okay. And then the coefficient of S1 is
18116.
And coefficient of S0 is
960. Okay, simply copy them. That's it.
Yeah, simply copy of this.
Okay, sir.
Okay. Similar for the numerator. Okay.
Sure, sir.
Numerator. Now, second question. I think who was asking?
Yes, sir. My name is Neha.
Yeah. Okay. Neha, what happens? Actually, if the model is of higher order model, let us say your higher order model is underdamped response, underdamped. The oscillatory behavior is there. So in that case, we cannot reduce to first order. Because first order system, there is no oscillatory behavior. Is it clear? Always the first order system is that is the O-damp type. Okay, there is no, this beta is always greater than 1. Always the response is no oscillatory behavior. Clear? So that means that higher order system cannot reduce to first order. Correct. So that higher order system can reduce to second order.
Yes.
But if you do second order means, let's say 10th order is there. If you do second order, matching will not be so good. If you go to third order, matching is better. So as we go to 8, 9, 5, 6, if you go to 9th order, matching will be very, very much high exactly. So it depend upon, because anyway, if you take 9th order model, definitely risk is there, but still you require more solution time, control size will be higher. So it is a one type of say trial and trade-off, whether you require less solution time or performance. So that trade-off should be there. And moreover is that again there are some techniques are there, they make you better and better results. Therefore, there are so many techniques are available for same problem. One technique give you not give better result, other technique with the best results.
Yes, sir.
Okay, so it depends upon the what type of techniques are here, what type of application are here. But the most important thing is that if the original system is of higher order, and it is of the nature of undertime type, oscillative behavior, you should not reach to first order.
Okay, sir.
First order decision should not be there.
Okay, sir.
I think point is clear, right?
Yes, sir. Yes, sir. Thank you, sir.
Okay. So now now coming to the unstable system. So now unstable system, what is say that if the system is unstable, system would say that okay, instability is because of not for all poles. Let us say that 10 poles are there. Out of these 10 poles, 8 are stable, 2 are unstable. So he said that he tried to neglect or initially 2 unstable poles. Keep only stable poles, then reduce the stable poles, and then unstable poles you can merge. The meaning is that in your actual plant, you cannot discard the unstable poles. Just like a dominant poles, we have to keep all unstable pole in our original Linux server model. Hello, Dr. Nidish? Is it okay? Clear what I'm saying?
Yeah, sir. Can you please repeat it, sir? Please.
What I'm saying, in the system, there are stable poles and unstable poles. Okay. So we cannot discard the unstable poles. Unstable poles should be a part of our reduced order model. We cannot discard the unstable poles at any time. So how to reduce the model? So he said that the unstable poles are you separate it first, keep only stable poles. So let us say we have 10 order system, 8 are stable pole, 2 are unstable. Out of the 8 you can reduce to 6th order, and the unstable pole which are keep separated, you must do the reduced order model. So that means the order become 8. That means each in the plant, the 10th order is there, and 2 unstable order there. You cannot reduce below 3rd order because the 2 unstable always been there. So this is the way he has explained. It is HS of the form PS, VS, QS, and PS, QS, and VS are the polynomial in S. These are the polynomials. So V of S is the product of poles with 0 or positive root pulse. So that we have to keep separate. And for this HS, we have to operate this sort of model. And then finally, 1 by V of S is to be multiplied. So this method is versatile. It is completely simple, requires no complex algorithm to reconstruct this sort of model of the transformation. So this is the one of the method of the Routh criteria, which has been published in 1978, and and there are so many methods that have been published earlier. That is called Pade method, time movement matching method, then mixed method, stability equation methods. So many methods are there. But this method comparatively very simple, and he is after that many issues that we observed in this particular approaches, and there are so many because time is limited is there. I cannot go further, or we are approaching 2 hours. So now these are things. But ultimately, I come last point is that this is the paper you can observe. Is it readable? Is it visible?
Yes.
Yes, sir.
So you can see that load frequency control, power CTY, intermodal control, and model order HTTP. You can see that in this particular research paper, I have used this Routh criteria, which was published in 1978 times. That time. So what I've said, this is I use in power history and some other application also. So here, this one method I told, so many methods are there. So the point is that these methods can be very helpful in your research domain also, because if you compile this one, or just like catalyst for our problem, is work as a catalyst, it will change our whole system. So maybe sometimes we get good result, because case simplicity, your control log is simplified. So there are many advantages are there which can be used. So,
Hello, sir.
so anyway, hello.
Yeah, sir. Can you explain the same reduction technique for an unstable system also with numerical example? Because
Okay, just give it. For example, let us say. Anyway, the keypad is not working, so I will explain to MATLAB only. So now numerator is there. Is it visible?
yes,
The
sir.
MATLAB screen is
Yes,
visible?
sir.
Okay. This is numerator 1. Okay. So denominator is convolution of say 1, 2 on convolution of say 1, 110, comma 1 minus 1. Okay. Sy is equal to transfer function numerator comma denominator. Have you seen the transfer function now?
Yes, sir.
1 upon, so unstable pole at S equal to minus 1. Okay. One pole at 2, another pole at one pole at minus 2, other at minus 10, other at plus 1, unstable pole. So now if you determine the response of this, take SYS. You can see system is 3.5 10 to 24. It is unstable now. Hello?
Yes, sir. Yes, sir.
So the unstability is there.
Yeah,
So
it
now
shows
what
that.
he said that, yeah, unstable. So what Krishnamurti said in the paper, he said you first of all separate this S minus 1, you separate 1 and minus 1. So that the transfer function, the denominator is only convolution of 1, 2, comma 1, 110. Sorry, 110. So what is this? Transfer function is S square plus 11s plus 10. The S is equal to transfer function 1 comma denominator. So now 1 for S square plus 11s plus, you have to apply Raoult criteria to this. So if you apply Raoult criteria, here 1 S square then S1. Here 110, 11, and here 10. So now your model is 11s plus 10. If you apply Raoult criteria to this, your model is 11s plus 10. So now what he says that your new transfer function becomes SYS1 equal to 1 divided by, just I am writing it, the pole at S minus 1, and here that is 11s plus 10. This is the Ritz order model. I understood this. Hello?
Yes, sir.
That is that the unstable pole you separate first. Take the stable poles, reduce by Raoult criteria, and then unstable pole that is S minus 1, that is Ritz order model, SYS R. So here R 1 divided by this separated pole, that is this is separated pole is pole S, this pole S minus 1. You can see these are merged to the stable pole. In other words, I am saying that unstable pole we cannot discard it in the model. It should be the part of the system. It should be the part of the system. Never we can discard this. I hope this is clear. Huh?
Okay, sir.
Okay, okay. So thank you for attending this my session. I have tried my level best to explain you the basic philosophy, logic, how that rotation, what are the challenges, practical challenges, and one method is there. It is not possible to explain all methods in one class, but the idea is given. So my point is that this moderation, although it is an old theory, but still can be helpful in our research domain. or when we start doing it, many challenges will come across. So that challenges can be solved. Or the other advantage is that whatever theory we are using here, sometimes same theory can be applicable in a control design also. That is also the one advantage of learning this model orderation concept. So if you have any further query, anything, you can also contact me through my email ID.
Sir, can you show that slide which indicates the rule for reducing the order for unstable systems?
Advantages. Which one? Okay,
Full slides.
1 minute.
Not this one, sir. Unstable system.
Yes, sir. I'm moving further. Yes, 1 minute. Yes, is it visible now?
Yes, sir. Visible. The previous one slide, sir. Previous one also.
Okay. Again, previous.
This one is okay, sir.
Okay. So anyway, there are it is not a say only
Thank you, sir.
discussion. Maybe any long discussion sometimes required. So you can, if you have any fundamental doubt on anywhere, you can drop a mail to me, and I will try to help you. And again, if you have good time, you can visit to IIT and you can visit to my office. Okay. Thank you. Thank you, Dr. Manmohan and your team for inviting me.
Thank you, sir. Yes, sir. Thank you so much, sir. Professor Yogesh Vijayhote, sir, for telling us about dominant pole concept and model order reduction using Routh-Hurwitz stability criteria through theory as well as a practical session on MATLAB. Thank you so much, sir, for your valuable insights. Thank you.
Thank you, everyone. Okay. Shall I leave now, Professor Dr. Manmohan?
Yes, sir. Yes, sir. You can leave.
Okay.